Hey, welcome everyone to the next lecture in the AI lecture series. Today we are talking about informed search, so let's dive right into it. So the key learning objectives that we want to cover today are the informed search, the concept of direction, how it applies to physical space and logical solution space, the concept of heuristics, greedy search, and A-star search, okay? So just to recap, the uninformed search, which is what we have studied in the past, is essentially a structured search, but it just does not have any way of knowing which way to go. So you might have, for example, it's an improvement over endless looping, but it's not intelligent. And the examples of the uninformed search, structured search that we studied last time was depth first search, breadth first search, and the UCS. And to recap, UCS itself, uniform cost search, UCS is essentially BFS, except it does take into account the weights or the cost of the edges. So if you have two different, so in the case of BFS, we would simply count how many edges we are away from the root node, and we would kind of go layer by layer. In UCS, we go almost layer by layer, but we take into account that if this edges has a weight of 10 and this edge has a weight of 5, then we will expand another layer here. So we try to keep the uniform cost around it, right? So it's almost like BFS, except it's taking into account the weights. And the UCS is a great algorithm. It's complete. That means if there's a solution, it'll find it. It's optimal. That means it will find the least cost path to it. And that is kind of intuitive because it will start from the top and keep expanding in every direction until it finds a goal node in order of the distance. So if you visualize this particular diagram here, you start from the start node and you keep expanding in a little circle by circle, which essentially is the contour of the uniform cost search, or all of these contours are at the same cost. And then it finally hits the goal node. So it will find the goal node, the least cost path to the goal node, and that makes the UCS complete and optimal. So it's a great algorithm. The bad thing is that it explores in every direction. So if we try to take a little visual here, starts from this start node, the goal node was here, but it's expanding along a big circle here until it hits the goal node, but it expands this area here as well, which is actually very far from the goal node. So it doesn't really have any information about the goal location. That's what we want to fix today. And that's a key idea we want to study today, which is called the direction. So the direction means that given two nodes, which one is in the correct direction? Which one should we expand next? So if we go back to it, so if we have two different nodes here, perhaps one here and one here, this one should be perceived to be closer to the goal node, and we should try to expand that here. So how do we do that? We need to use certain search heuristics. A search heuristic is what we use to expand to estimate which one is closer to the goal node. So essentially a heuristic is a function that estimates how close a state is to a goal node, is to a goal state. And based on the heuristic, we decide, okay, between these two nodes, which one of the candidate states is closer. That gives us the sense of direction. Just kind of like when we hear somebody, we say, okay, we hear somebody and we perceive the direction to be coming from the right side. So we go that way, we don't go left side, right? So this is exactly how it looks. And the heuristics are not perfect. They're designed for a particular search problem. We'll talk about that in a moment. There are many different examples. We'll study that as well. But I want to point out that heuristics are not perfect. They may help you down the right path, or they may also help you down the wrong path. As you can see in this example here, if we look at these two candidate nodes here, both in red, and you see that this one, the Pacman, the agent, might think, oh, this one looks closer to the goal node. It'll take that, except we can see visually that this one is actually closer because this one will come here, but there's no way to cross this boundary, which the search heuristic may not be aware of. So search heuristic is just an estimate. The estimates are not perfect. So it might think, oh, I'm only 5 meters away, but in fact, it's not 5 meters away. It has to go back this way and come back. while this one thinks that it's 10 meters away, and it's pretty much 10 meters, maybe it's 11 meters away because it only has to come down this way, etc. So that's the search heuristic. A search heuristic gives us a concept of direction. Once we have a direction, we can then use a greedy search algorithm, which is now informed. So when we say it's informed by the concept of direction. So it's informed by which one it seems to be closer. So that's the information we are referring to. So once we have the concept of direction or the information, then we can use a greedy search to say, we can expand a node that we think is closer to the goal node, and we can keep going on from there, expand, see which one is closer, and go there. Now, again, because heuristics are not perfect, this best first approach, this greedy first approach, or greedy approach, may take you straight to the wrong goal. Wrong goal means that it may find a very long path to it. This is not UCS anymore. We're trying to use a greedy search, and this may not find may find a long path. So in that sense, it might act like a badly guided DFS. It's like a DFS, except it's going away from the goal. Eventually, it'll still hit the goal, but it's just going away from it, right? So that's a greedy search here. And here's an example of it. Let's study this example here correctly. So we have this is our start node here, and we have these two candidate nodes here. Both are at a distance of 2, but this one estimates that it's at a distance 3 from the goal node. This one estimates that it's distance 5 from the goal node. And we can now see that this one is actually 5 whatever units away from the goal node. This one thinks it's 3, but actually then you see an edge for 10, and this one still thinks it's 3. So we say, okay, we now have an option between this one and this one. So we say, okay, we're gonna take this one because it's only 3 meters away by the estimate. This one thinks it's 5 meters away. So we can take this one. Again, we go 10 meters, and again, it thinks it's 10 meters, 3 meters away. We again go 10 meters, takes 3 meters away, and again takes 10 meters, and you can keep building it. Now you can see we've already come many, many, many meters here. And finally, we see here that this is now how many? 62 meters, while this estimate was actually correct, and we could have gotten there in 5 meters. So greedy search, it might have the right intention, but it has no guarantee that it'll actually take you down the right path here. So that's what we wanted to cover about greedy. So if we compare UCS and greedy, they're interesting. UCS and greedy essentially orders the contour by the cost. How much cost, how far away are you from the start node? Doesn't know anything about the goal node, goal state. Just says how far are you from the start node, because it wants to expand in the order of the distance from the start node. That's the contour. That's the uniform cost. So it wants to go uniform cost. First, it'll expand everything that's 1 meter away, 2 meters away, 3 meters away from the start node. So it only has its mindset on the start node. Doesn't know anything about the goal node. So the UCS is saying, okay, from my, essentially, if we can picture a string. So firstly, we expand the string, and we run the string from the start node 1 meter. We don't find the goal node. We expand the string to 2 meters, expand the string to 3 meters, and keep expanding the circle. That's the uniform cost. Greedy only looks at how close am I in my estimate to the goal node, and then it tries to go there. So it's not that either approach is bad, but UCS doesn't take direction into account. Greedy doesn't take path cover distance into account. In the best idea here is we should simply combine these two ideas. Both ideas have some merits. We can combine these two ideas, and that's the key idea. The key idea here is the A-star algorithm, which is a new algorithm. And what the A-star does is it comes up with a new ordering, which is defined by the sum of G of n, which is the backward cost, which is what the uniform cost the UCS is using, and the forward cost H of n. So it takes the sum of it, and then it expands the goal, it expands the node as per that. And why is it a good strategy? It's a good strategy because it does keep an eye on the start node where it started from, but at the same time, it does use the estimate into consideration, takes that into consideration, and see which node it should expand. So that's a key idea here. And the key idea within A-star often is the design of heuristics. that is the main point of improvement. We will study A star, we'll study the specific heuristics in another mini lecture in a bit. But the key idea here is that A star is A star. A little pun on it has kind of like the A star grade. So A star is a very good algorithm. But when we have a new problem, you need to design new heuristics, because A star algorithm simply orders by the sum f of n and g of n plus h of n. But the h of n are the heuristics. That's the heuristics that we studied, which the greedy algorithm uses. And that's what we have to come up with. And that's what we'll be studying more later on. But that's the key idea here, is the A star. And we will study that the heuristics in another lecture. Keep learning.